Welcome to Thursday Dairy Update. This is Kathy Barrett with the Cornell ProDairy program, and along with Dairy Business, we're pleased to be able to offer this webinar series. This webinar features Dr. Mike Van Amburgh, Professor of Dairy Management at Cornell University, and he's going to be talking to you about the Cornell Net Carbohydrate and Protein System, newest version 6.5.
We just released 6.5 in publication. And not that it's described in here completely, but we also just released a version, what we're calling 6.55. After the release of 6.5, we found some things that the model wasn't, we're always correcting errors and doing edits to the feed library, but some other things that came to light with immediate feedback from the field was that heifers were still getting fat, dry cows were getting fat, and it wasn't really working for pasture-fed or high-forage-fed cattle. So we made one more update recently, and that's starting to hit the field. Some people are delaying that until they work through some of the logistics of it. It really has to do with passage rate, and I'll share that with you. So there's a little bit of all of that in this presentation. So just briefly about feed chemistry, amino acids, a little acronym stuff with ANDFOM, and a little bit on UNDF. Rumen ammonia passage rate, some things about the UN assay, and take-home messages. So one of the big changes, those of you who may be old enough to have been weaned on CPM dairy in our early versions of the CNCPS, were always told that we needed to keep a lot of peptides and nitrogen in the rumen to make sure we had enough, could make enough microbial protein. And that really, we also characterize our feed based on NPN. And what we've, just to summarize quickly, NPN doesn't really supply MP in the CNCPS, and it's not a very clean chemical fraction. Labs don't provide it and on a routine basis, and the assay is really messy. So, just some nomenclature things. So we converted the protein A1 pool to ammonia. All labs will measure ammonia, put that out routinely. It's a very discrete measurement. And what we realized, and I'm not going to show you all the data today, but there's been a lot of data published in the last at least 10 years to demonstrate that those small peptides and free amino acids that were previously characterized as NPN actually have a lot of biological significance if they escape fermentation. And because they are soluble, they flow with the liquid passage rate, or flow with the liquid, which is much faster than the solid. And in fact, what you find is that up to, in some studies, up to 12 to 15% of the total amino acid supply could come from those small peptides and free amino acids. So A1 has been recharacterized as ammonia, and anything that's soluble in the rest of it is considered true protein, and that goes in the A2 pool. So now we have A1 and A2, which is also consistent with the soluble pool, because in the past we had A and then B1 and B2, and that didn't really split the definition of solubility exactly the way it should be. So we've made that change, and that update seems to be working well. That would make a feed look like this. So if you looked at corn silage, just the protein side of it, in the old library, you see that very large A1 pool. That would be the NPN as it was previously characterized, and the rest of it. Now what you see is the ammonia as the A1 in the new library, but a very large soluble true protein pool. And this doesn't always work, right? We could have nitrates and nitrites and things like that in there, but if you've got that problem, you just need to analyze for it. But you can see how that changes the characteristics of the feed. The same with the B1. Right, proteins, they change a little bit along with the B2. These updates really seem to make pretty good biological sense when we're feeding cows, and the cows seem to respond better to this in all the feeding studies that we've done to kind of verify this chemistry. So the other thing that was done, and this was a long-standing issue apparently, and I obviously inherited this, the soluble fractions of feeds previously were associated with a solid passage rate for some reason. Anything associated with the feed was tied to the solid passage rate, and we reassigned everything that was soluble, both sugars, starches, carbohydrates, the soluble proteins, to the liquid passage rate. And that really has a substantial impact on the rumen balance of nitrogen and things like that. So ammonia production went down significantly. Again, that had to do also with the NPN. But we get more MP now from the soluble protein pool, especially with high alfalfa diets. I remember a lot of users would call me up or write me email and say, why, if I'm feeding 22% crude protein alfalfa, does the model still suggest I need to add soybean meal to meet my rumen N requirements? And I could never fully understand how to answer that until we got into some of this chemistry and the passage rate. And once we characterized this, and that concept, that all kind of fixed itself. All right, what you get though is you get more MP, which is why we can move to lower protein diets. And it looks like you get less MP from bacteria, but that's really just a dilution effect. All right, the actual yield doesn't really change that much. All right, so the effect of this, the increased passage rate of the soluble, the RDP drops because you're pushing more of it out of the rumen. The KD of the A2 pool, the RDP was decreased. Right, we had that over-evaluated. We were at 200 to 300% per hour, and that really should be down in the 40 to 60% per hour, and that's where it's set. Sugar KDs came down the same way, so the rumen nitrogen demand decreases a little bit. Does knock down, with those KDs going down, it does knock down microbial yield a little bit, but the amount really isn't that much in the end, and it kind of corrects some of the other problems. So the model's a little more sensitive on predicting protein supply, again, which is how we're getting to some of the lower protein diets. The other big change, and this was really significant in the first big chunk of what Ryan Higgs did for his PhD work, and that was to look at the amino acids. The original library was developed, published in '93, had not really been updated. We were using methods back then that didn't really help us get at the sulfur amino acids. They weren't using a pre-oxidation, so a lot of those were oxidized. And, some feeds have been updated over time, and then other feeds not. So we had new and old methods in the same library and a lot of inconsistency, and with everybody trying to move to amino acid balancing, it was causing us some problems. The biggest problem was an underestimation of the methionine content of the feeds, which caused us to want to put a lot of methionine in the diet. You still want to put methionine in the diet, but until we got the feed library fixed, we really didn't know what direction we were going. So the amino acid profile of every feed in the library has been updated. We got data from assay and VONIC. We took some from the NRC. Also had some internal data from work that Debbie Ross had done over time, and a little bit with Charlie Sniffen and some of the work he did back at Michigan State. And in many cases, amino acid profile are very different from what was in the library due to the analytical methods used. They've been really updated since that original library. Now you can see, if you look down this slide here, alfalfa hay, in many cases almost a doubling in some cases of the methionine content of the forages. Blood meal didn't look remarkably different. The soybean obviously had been updated at some point in time. The canola meal needed to be updated, so you can see some change, quite a significant changes in some of the methionine content of those feeds. And if you look at other things like lysine, in some cases lysine went down, in other cases lysine went up. So we saw lots of changes throughout the feed library for all of the amino acids in the feeds. So again, cleaning it up, newer methods, more robust, more correct actually, and consistent with what we currently know in the current method. So all in all, that was a big improvement, but that creates offsets. Right, when you start changing things like the methionine, and now we're pushing more methionine down the gastrointestinal tract because of the increase in the feed content, something's got to change. So the downstream effect then is to look at, well, how do we have the characterization of the efficiency of use set up? And we've been using static efficiencies for years. There was some PhD work done, a little over 10 years ago now, in Canada, and then Helene Lapierre reevaluated that same data set and published it in a CNC proceedings in 2007. And I immediately took notice of that and was trying to figure out how to make use of it. The way Helene had done her mathematics, though, is that she looked at the system as a percent of optimal supply on an MP basis. So as you underfed the supply of amino acids relative to MP, the efficiencies went up, and you can see that in the column at 75%. And then as you moved to 100%, you saw the efficiencies go down. And then as you move to overfeeding of MP relative to the requirement, you'd see each amino acid efficiency go down even more. And my long-standing perspective on this is that the efficiency of amino acids really wasn't a function of the MP supply, but it was really a function of the energy-driven protein synthesis that you had in the cow. So we elected and assumed that at this 100%, ME and MP was basically balanced. So this was these were the efficiencies that we then adopted for use in version 6.5 of the model. So you can see here the efficiencies of use. And prior to 6.5, we had a split relationship between on the amino acids between maintenance and lactation. And again, with lots of conversations with Helene and in our own thinking, we could not figure out how to separate those things effectively. I didn't know how to do maintenance and lactation separately in a high-producing lactating cow, so we combined them, again, using those 100% efficiencies, and you can see what that looks like. For example, methionine went from 100 to 66, lysine went from 82 to 69, arginine from 35 to 58. You know, and some people have said, well, if you multiply it through, does it work? Well, sometimes it works, but most of the time it doesn't. So you can see that we have very different efficiencies now, and that changes some of the requirements. Now, the question here is that does it change the requirements? And because of how this technology works, I can't really talk through the slide the way I wanted, but you can see that if you use the old efficiencies with the new supply, you get this grouping over here where and this is a study of, these are all the studies that were available where we could look at, where we knew there were deficiencies, looking at metabolizable methionine as a function of the total MP versus the methionine balance, which is supply minus requirement. And when doing that, that line should cross 0 down here on the balance. And you can see using the old efficiencies, in all of those studies, there was never a deficient diet. We knew that wasn't true. Using the new efficiencies, you can see that it actually does a nice job of spanning the supply side, and that we did have deficient diets, but we also had diets that were balanced to excess on methionine, and that makes more sense to us and told us that this new efficiency was actually a step forward, especially when we coupled it with the library values. The most important thing here is to look at where it crosses the line. The intercept here is 2.6. So hang on to that. That's pretty important because you're going to see an entirely different mathematical approach that gets us to basically the same number. So what we're getting to here is that the model may be remarkably different, but it's internally consistent using two different forms of a mathematical approach. So if you go back to balancing for methionine, here's milk protein yield on the y-axis, and digestible methionine as a percent of the MP on the x-axis. You can see that the break point was 2.34. And then if you use the updated profiles and efficiencies, what you see, same response, milk protein yield response in grams per day, the break point is at 2.6. Okay, well, we were thrilled to see this. This is the way that Andre Roelquin had set this process up, and then Chuck Schwab had continued using this kind of broken stick model. And we were happy to see that the broken stick model gave us the same breakpoint as what we think is a more robust way to do it, and that was this type of calculation here. So to our satisfaction, we were getting the same answer two different ways. In practical application, and I think this is the point that I want to make to everybody who tries to balance for amino acids, running all of this data against ME for version 6.5 and version 7, quite frankly, and I don't want to talk about version 7 today, but we have been working on version 7, which is an entirely different modeling approach than anything else we've done. We get to this 1.12 to 1.15 grams of methionine per mcal of Me as a more of a gram approach. So, and I'll give you an example of how to use that. But we've been suggesting to people now that maybe that's the way we should be doing it, and not just looking at this ratio of lysine as a percent of MP, or sorry, methionine as a percent of the MP. And then if we look at lysine in version 6.1, we were at 6.93 on the breakpoint. And if we look at version 6.5 with these updates, we're now at a breakpoint of 7, which is actually getting closer to what some of the ideal data had been from some of the early studies around 7.2 to 7.4. So as we keep evolving this, these breakpoints get closer to where we think some of the ideals are at. All right. So, but if you come back to the gram idea, so if you're balancing a diet and you're at 60 mcals of metabolizable energy, then, if you said, my minimum is going to be 1.12 grams of methionine per mcal of energy, then I need about just over 67 grams of methionine, metabolizable methionine, to meet the requirements of that cow. And then the way we're telling people to do this is then look at the lysine requirement, and the ratio was, 2.6. So you would go back and say, okay, I need 2.7 times that 67 to get my lysine requirements, and now I should be about 181 grams of lysine to meet the lysine requirements of that lactating cow. And again, there's a little bit of management around that, but for the most part, this has been working reasonably well, and people who want to balance for amino acids always calculate the methionine first. That's what the gram of amino acid to energy relationship was derived on. Never start with the lysine and work backwards. Always start with the methionine and work forwards if you're going to try to do that. If you try to do it on the lysine, I think you're going to get incorrect values, because we still don't really know what that lysine to milk ratio is in 6.5. We get a better handle on 7, but I don't want to work backwards on it right now. I'm going to skip this slide. So the other thing about amino acids and use of the model, the one thing that we found is that people are out there trying to balance for amino acids, and they're looking at milk volume and sometimes saying, hey, I don't think this is working right. So what we're encouraging everybody to do is look at energy-corrected milk. So when you're formulating for amino acids, everybody should be balancing on energy-corrected milk, because you don't really know what the cow is going to do with that amino acid carbon. She could use the amino acid as an amino acid, but she could also redirect that amino acid carbon to something else, and kind of an anaplerotic type reaction, and then you're going to get a different outcome, right? So if you use energy-corrected milk, you capture the milk volume, protein, and fat yield changes. That's almost always easier to detect than a single particular milk composition change. Some people will say, well, I'm going to feed amino acids and get more milk protein. Well, maybe not today, maybe not with this cow, and maybe not with this diet. So I think that provides better information for this type of outcome, and it gives us probably better ways of answering whether amino acid balancing is working or not, instead of just looking at one parameter. The other thing that's coming, and this is starting to show up on the forage summaries, forage analyses you're getting from the laboratories, and that is the NDF analysis. And this is partially related to the model and partially just related to good nutrition. Thanks to Mertens, we got the publication in AOAC and the approval for NDF as a characteristic for feeds. And luckily, he published all the relevant methods for NDF. The one that we're trying to move everybody to is this one right here. That's ANDFOM. So you're going to use amylase, sulfate, sodium sulfite, and ash correction. All right, and this was discussed actually back in 1992 in the original publication by Charlie Sniffen. but somehow it just wasn't followed up on, or nobody paid attention to that particular aspect. And what I came to find out is that out of Pete's lab, out of Ansu's lab, whenever Jimmy Robertson was running NDF, it was always ash corrected. And he used to get after me about that and tell me, why aren't you telling everybody else to do that? And I guess we're finally catching up, 20, 30 years later. So why is this such a big deal? Well, I think it's a big deal because I've been, I get questions from the field about why aren't the cows performing right? Why do we have variable intakes? Why do we have subacute ruminal acidosis? Why is there milk fat all over the place? And some of the things that we've determined is that it has to do with the type of forage equipment, the type of soils, and the speed with which you're moving today. Right? We've got this wide swathing that encourages picking up dirt. We got these big choppers that move fast and make dust and dirt fly. We've got flood irrigation in various parts of the country, and that causes problems. And that dirt and or soil doesn't solubilize in the MDF solution, thus is not corrected. It inflates the NDF content in the feed, and that means that the diet that's formulated is lower in actual NDF than what you think, and that means that rumen health can be compromised. And that's really how I stumbled on this with a herd in Arizona that just had real problems. And after a couple months of sorting this out, and after we ash corrected the NDF, they had sandy soils, big equipment, went fast. They were underfeeding NDF by about 4 or 5 units. And once we got the true NDF up to where it was supposed to be, all the acidosis, all the milk fat, all the intake, all the fecal inconsistencies went away. And here's just one example of that. This is taken on a farm in Texas, and you can see that chopper running, and you can see lots of dust flying, and a lot of people in the Northeast would say, well, that's got to be the feed. And I'll tell you that is not the feed being dry and dusty. That feed's actually pretty moist. That's the soil. All right, and this was a herd that was having problems with intakes and inconsistencies and subacute ruminal acidosis. And we got called in to kind of help them, some alums that were managing the farm, and they said, can you help us sort this out? And we did. And if you looked at some of the analyses, these analyses that came back, you looked at the ANDF-OM coming from one field, or the ANDF, it was 60.2, but the ash corrected was 55. So there's about 5 units difference in NDF in that, which means we had quite a bit of soil contamination, and you can see that from the picture. You looked at one of the other fields, it was actually 10 units. All right, so this is your primary forage, and again, this might not be in a region of the country that affects some of us here in the Northeast, but even the Northeast has some of these issues. If this is your primary forage and you think you're okay on NDF, you could actually be several units off on a TMR, and that could be causing you problems, and it goes unknown. But this also plays into the idea of, well, what do we do about rates? What do we do about digestibility? And if you don't have that right and your NDF is off because you've got this contamination, then your energy values actually aren't being predicted correctly either. So this actually plays into all areas of the model in terms of what we're trying to do to predict amino acids, energy, and things like that. You can see that this is a slide from Cumberland Valley a couple years ago now. This is the NDF ash and hay crop silage, and anybody who knows what a normal bell-shaped curve looks like knows that this isn't a normal bell-shaped curve, and we have quite a tail on the high side of the ash content. Again, just demonstrating that we have some samples that we have pretty high ash, and that those would be the ones that you're really worried about. Again, this is a few years older, but the NDF ash and corn silage from 2012, and there's actually nothing on the left-hand side of the curve, right? But that's a pretty low number. But you can see that you got quite a tail going out. So is there a problem with all the samples? The answer is no, but there are some samples out there that have quite a bit of ash, and those are the ones that we have to worry about. And if that's your farm, or if that's the farm that you work with, then that's something that we need to pay attention to and get the right value for, so we can get the right outcome. And then, this I think is pretty telling too. We get into this whole concept of, well, does this affect anything else? Well, it does. You can see here we've got 2 samples where NDF was about 55 and ash corrected 48, 60, and 50. There's a 10-point. If you look at the NDF D at 30 hours or at 56, but if you ash correct, it's actually 66. Right, so when you're thinking about digestibility and cow behavior and microbial yield and rumen nitrogen requirements, not having this correct is really going to throw everything off. Same thing here. Right, so this ash correction is not just to get the NDF content right, it's to get all the other estimations and the use of NDF through the model correct so we can get the appropriate energy, get the appropriate microbial yield, make sure that, and rumen health, obviously rumen health is going to come first on all of this. So these things are important. Again, this is going to vary by where you're at in the world, where you're at in the U.S., and the type of soil that you have and the type of equipment that you have. But standardizing to this type of method cleans up all of that so then we just don't have to worry about it. So some other things that have happened, again, so moving away from that, we'll get to the idea of crude protein. With updates to the model, with high quality forages, good cow comfort, we know we've got diets that can be formulated at less than 15.5% crude protein. There's no magic to that number other than the fact that when you get down around 15 or below, that scares a lot of nutritionists. And I know when I talk about this out in the upper Midwest, they shake their heads at me and say there's no way you can make that much milk and that kind of protein. And partly that's because they've got a bunch of really high quality alfalfa that they're trying to work around. But the truth is that the cow can do that. If everything is right, we're doing that right now. Matter of fact, Sam President told me, we've got a diet running down around 15 right now, and it's in the high cows, and we got cows hitting 160 pounds of milk on that. So, we're at 14.8 actually. So cows are remarkable that way, but it's how the protein comes together. The big thing is that you got to make sure that rumen nitrogen balance is positive, and in some cases MUNs can be used as a proxy for this. But cow comfort, the reason I'm bringing this up is that the model will allow you to do this now, and I'll talk about why that is here a little bit. Some of it's what I've already explained about the feed chemistry and the NPN and things like that. But when you get to that point, making sure that everything around the cow is correct, the feed delivery is good, the cows are happy and healthy and comfortable, and they can eat when they want. And we're learning that really impacts their nitrogen metabolism in ways that I guess even I not represented, but misunderstood or didn't appreciate. Then it comes to the idea of some safety factors, because we've had some situations where somebody went out, formulated lower diets, but had groups that were overcrowded 20-30%, had a time budget for the cow that wasn't great. Cow couldn't eat when she wanted to. That kind of screwed up her nitrogen recycling, and we had cows that were acting like they were nitrogen deficient, not because the diet wouldn't allow it, because everything around the cow wouldn't allow it. And there's lots of other things that happen like that. One of the things that we've also run into, and just some benchmarks, if the MUNs are calibrated appropriately, any group below an MUN of 6 would suggest negative rumen nitrogen balances. I'm a little concerned sometimes that the labs don't have the MUNs calibrated that low effectively. So I like PUNs more. What I do know is that anything below a PUN of 6, the whole body pool of urea nitrogen is too low to effectively meet the needs of the rumen through recycling. So the rumen's going to end up being a negative nitrogen balance. Feeding behavior due to things like overcrowding will impact that balance, and then that gets us into trouble. And because the rumen nitrogen balance and recycling is integrated over a 24-hour period in the current version of the model, I think that's where we get into trouble. So I think some monitoring of particular cows, either groups of cows or cows within groups, is important. The bulk tank is way too insensitive to make this analysis, especially on some of the larger herds. So again, if you're going to start following the model and make sure, and it says, hey, you know what, with these forages you can be down below that 15.5, I will tell you, not that you shouldn't do it, just make sure you're monitoring appropriately so you don't get cows that run into problems, especially if there's some other constraints like budgets and overcrowding. And you can see that here. This is actually from version 7, and I only show this as an example. Basically, because version 6, again, does it over a 24-hour period, we don't have these kinds of fluxes. but this is an example of where version 7 will be more informative. You can see this blue line is where we have continuous intake and that the rumen ammonia balance is consistent at just over 6. But cows don't eat like that. So if we, in version 7 needs an intake pattern to work effectively. So if you feed the cow 8 times a day, so we're going from continuous to 8 times a day, you can see this pulsatile behavior here of rumen nitrogen balance, which is a little probably more like it really happens. But if you go to 4 meals a day, which is really getting closer to what a cow would do, you can see we get quite a flux over time in that you go down, towards that 5. And the only reason the bottom of these graphs don't keep going down into the negative is that in version 7, we actually say once you get to 5, you're in the rumen nitrogen deficit, and we shut the bug growth down so the demand goes down. Otherwise, if we let that run, these would go negative, and the rumen's probably in trouble. This is just showing that feeding behavior around the time budget will have some impact on this. So we have to be a little bit careful when we go to these lower crude protein levels if the management of the cow is such that the cows cannot eat when they want to. It's the same kind of thing for all conditions around rumen health. All right. The one thing, as I mentioned earlier, and this gets to version 6.55, that's what we're calling it, is the NDF passage rate and the ME and MP predictions. The 6.5 used KP equations from Terry Sayao and his PhD work, and that's the same database used to develop the 2001 NRC equations. Those equations generally average about 0.04% per hour as a rate with a range of 1.3 to over 7. And what we've learned is that for dry cows, heifers, and pasture-fed cattle, those predicted passage rates are too high and causes an underprediction of ruminal digestibility and ME and MP supply. And we had cattle that were doing a better job digesting that forage than what we were predicting, and it was underpredicting their MEs, and they were getting fat. So that's why we're doing this, making this change. So we upgraded the equation. You guys don't really care about the math so much, but there's the equation. And if you look at the predictions from that equation, it's from the NOR4 model, which is a pretty good, we like this equation a lot. We've adopted it for many things. You can see that the passage rates are like 1.2 to 2.9% per hour, so it's quite a bit lower than anything that we're getting with the previous equations. It does a nice job of kicking up the energy available, especially from things like dry cows and heifers. But again, like all things, there's always an offsetting error. We had to go digging. So you fully utilize that NOR4 equation, we had to look at post-ruminal NDF digestion coefficients. And that coefficient's been set at 20% since the inception of the model, so that's a long-standing intestinal digestibility. Did some digging through the literature. There's not a lot of data on this. There's some from Joanne Siciliano-Jones back from her PhD work at University of Illinois. More, and that was in this 3 to 5 range. If you looked at the work from Cornell and Broderick, 2005, that had it in the 3 to 5 range. So what we did is, at this point, we've done a global switch to everything except the proprietary feeds, and so the library's down to 5% intestinal digestibility. So if you take, this just happens to be a diet from one of Brittany Sweeney's studies on transition cows. It's something that's not published yet. Pretty conventional diet, high straw diet, about 32 pounds of intake. Cows about minus 21 days prior to calving. And you look at what was predicted or what the cows actually did. They didn't really change on body condition score, and they didn't change on body weight. All right, so in reality, these cows were pretty much at zero energy balance while still growing their fetus appropriately and doing all the things that we want those cows to do. But if you look at the predictions of the model, here's 6.5 in terms of ME and MP versus 6.5 or 6.55 with the NOR4, you can see about 1.5 mCals more ME and about 80 grams more MP from that prediction, and that kind of fits with what we think is going on there. If you look at the maintenance requirements and some of those changes, and you look, basically you get down here to the bottom and you look at the overall balance. The prior balance was minus 3 mCals, so you would want to put more in if you were actually balancing to 0, whereas with the Norfolk equation, it gets us within that 1 mCal, and given that the total now is at 31, we're pretty comfortable that we're getting closer, or 32, that we're in much better shape in terms of our energy prediction, and it gives us a little boost in protein. And I've been suggesting, at least 1,300 to 1,350 NMP, so this gets us in that range. So just an example of how the change in the KP equation has affected the dry cows. And actually, if you just look at the other thing that it's helped, and Ryan Higgs just sent this to me last week, he took this and reran a bunch of data that we were struggling with from a bunch of pasture studies done both here and in New Zealand. And you can see that if you look at observed milk versus predicted milk using this new passage rate, I can tell you the slope bias on this before was about 30%. And there is no slope bias on this now. So making that change on the KP for pasture-fed cows primarily in New Zealand really cleaned that up. So that Ryan was very happy to see that. He's back in New Zealand now, and now he has the ability to actually move ahead using the model in pasture conditions, because we were trying to figure out why it wouldn't work on those pasture cows as effectively as we thought it should. And it all had to do with that passage rate. In the intervening time, one of the other things that happened, people were implementing these lower protein diets, and as you get closer to the requirement of the cow, you actually start to find some of the problems with feed chemistry, characterizations, and things like that. And one of the things that happened along the way is that we ourselves were implementing some of these lower protein diets, and some of the nutritionists in the field went out and started to do the same thing. And what they found is that it didn't always work. And I was getting some pushback, and people were saying, "Hey, Mike, I'm not sure that you got this right yet. Why did the cows crash when I made this change? You said it should work." And not all nutritionists want to give up their diets. They don't want me to see what they're doing, or they don't want to admit that something went wrong. And most of the time, it has nothing to do with the nutritionist, and it has something to do with the feed characterization. And in fact, that's what we stumbled on, is that some of the things that people were putting in cows didn't have the intestinal digestibility that was represented in the feed library, which led to this idea that it would be good if we actually came up with an assay that we felt comfortable with, giving us a prediction of total tract nitrogen digestibility. And we had run the modified 3-step many times, but didn't feel comfortable with the output of that, because we started to recognize that there was quite a bit of sample loss from the bags due to some of the types of feeds that we were analyzing. So Debbie Ross spent 5 years, we spent 5 years together working on her PhD trying to come up with a better assay, and we did. And so we have this new assay, and then the reason I bring this up is because one of the things that we're recognizing is that for non-forage feeds right now, ADIN is probably not the right input to get at unavailable nitrogen. For forages, I think Pete's probably still right, that will serve as a reasonable proxy, although we're in the process of testing that now. But for all the non-forage feeds, especially for things like blood meal and some of the protein meals, ADIN looks like it doesn't actually give us the right value. So we're starting to develop this value, this assay. We're starting to use this assay and adopt the assay for using it in place of ADIN. There's been lots of work done on it. I'm going to move a little fast through these slides in the interest of time. The bottom line is that, like all things, we do it, we evaluate it, we do it, we evaluate it. We look at things where it works, feeds where it works, and feeds where it doesn't work. High-fat feeds is causing some problems, so we're working to figure out how to add either biosalts or lysolecithin to emulsify to help the lipase activity for high-fat feeds. Protein samples, we received a bunch of keratinized proteins and had some mixed results. So we're looking at some of the enzymes, and are there enzymes missing that would work on more keratinized proteins that the cow would naturally have. So we are exploring some of those things. Bottom line is that when we look at things like blood meal, we can take a really high quality blood meal and take the same blood meal and throw it in an oven and have the same nitrogen value, and you can see here's the ADIN of that blood meal as it's intact and then heat damaged, but then look at the prediction of the assay in terms of indigestible nitrogen and see that there's 16% indigestible nitrogen through the assay or 93 on the heat damaged, and ADIN is not going to pick that up very effectively. And the same thing with some soybean meal. You can look at a solvent-extracted soybean meal or heat-treated soybean meal, and you get basically the same ADIN. When the assay, you run through the assay, you see a little bit of a spread there indicating that, when you do heat-treat that soybean meal, you should see more damage and more bound protein, and in fact you do, and in many regards that's helped us out a lot. We decided we better put our money where our mouth is and test this in some cows. So we used 2 blood meals. That was basically the only difference in the study. And again, trying to figure out, can we use this assay to get a number in place of ADIN for some of these feeds that really don't fit detergent chemistry, and does the cow really care? And 128 cows, 8 pens, did all the things we need to do to run the study. There, the diets, the biggest difference in the diets was the amount of blood meal that we put in. The lower quality blood meal, the stuff with the higher undigestible nitrogen, was lower in total nitrogen, so we had a little bit more, but in the end the diets were isonitrogenous, isocaloric, iso-NDF, iso-starch, so everything else was good. If you look at the nitrogen intake across the treatments, we had pretty similar nitrogen intakes across the 9 weeks of the experiment. What was fun, though, and remarkable to us is that the moment we put the cows on those treatments, the cows on the high UN blood meal actually dropped in milk immediately and maintained that all the way through. And I don't have that in these slides, but in the end, the total nitrogen intake was about 675 grams of total nitrogen. The difference in digestibility was 32 grams. All right, and the other thing that was interesting is that the MUNs and the PUNs were both different on these cows. So you couldn't detect the difference in digestibility through just the milk. We detected more differences in digestibility if we looked at total whole body nitrogen metabolism along with the milk, and that was really intriguing to us. So the cow, basically what it said is that the assay is very good at picking up some of these differences in digestibility, and that we could balance these diets within 5% of their total nitrogen requirements and actually pick up this difference, because that's really about what the difference was between these two treatments. So it says the assay and the model together can really help us fine-tune some of these diets, and again that comes back to the safety factors I talked about earlier, because then you'd have to really think about, can I implement this diet on this farm given everything else that's going on around the cows? In the few minutes we got left, the other thing that we've done is made the model more robust in terms of looking at the environmental impact of the cow. Right now consumers want more environmentally friendly cows, diets, food, things like that. There's lots of questions from people coming from everywhere about the environmental impact of food production, dairy production, cows, and things like that. So we've continued to set the model up to look at nitrogen excretion, phosphorus excretion, and then we've moved into things like CO2 and methane. And so we have fairly robust predictions. This graph here is really just literature data and or data from our own experiments at Cornell, where energy is held constant or first limiting, and then we looked at the effect of nitrogen intake on milk production. And in this case, there's no difference in milk production. There's really not much difference in fecal nitrogen excretion, but you can see that urinary nitrogen excretion changes quite dramatically. So this kind of data tells us that if you want to reduce the environmental impact, get rid of the protein that the cow doesn't want and she's going to pee out. And we've included that, so we're looking now at this productive end, the total end, productive end to urinary end relationship, and that's helping us in the field improve the nitrogen efficiency of cows on farms. What we're telling everybody is we want to be 1-to-1 at least, and if you can balance effectively, you can be in that 1.1 to 1.3-to-1 range, and there are herds that are effectively doing that out there. That doesn't always increase your overall efficiency because some of that's energy driven, but at least gets rid of the protein that the cow says she doesn't need. And then again, we're some of that same output. This example, we're at 1.4-to-1, and that's a real herd actually. But then we're getting into the methane and CO2 predictions and the ammonia potential per cow from what she excretes every day. So this, now we're giving people the ability to actually predict, we're giving nutritionists or anybody who wants to use the model the ability to predict how much methane per day or how much methane per unit of milk is being put out, and then also how much ammonia per cow should you expect to volatilize per day based on her urinary nitrogen excretion. And if we look at the other thing we put in there is CO2 production. We had lots of questions from people. Somebody says, why do I need this? I don't get paid for this. Nutritionists don't really care. But there are a lot of policymakers out there and a lot of people in the world who do care. So we wanted to make sure that we had this available to everybody so they could answer this question if it did come up. So you can see that the model does a reasonable job of predicting the amount of CO2 produced by these cows. There's 5 studies and 22 treatments compared to what the study predictions were. And you see the same kind of thing with the methane predictions. So the model's doing a reasonably good job of predicting methane and CO2 relative to, along with everything else, the energy and the protein. So this allows us to give an environmental snapshot of the diet so every nutritionist can have this in their hand now. And I think over time that will be useful as we have more of these conversations. And then like the data that Capper and Bauman and those have showed us many times over, as you make more milk, you actually reduce the environmental impact, and milk should really be the object here. And this also helps you have that conversation. I did this in Ireland about a month ago, where a bunch of producers said, hey, our pasture-fed cows are more environmentally friendly, and I said, I'm not sure that's true. And so we brought this data up, and after I showed them this, they didn't recant, but they understood what I was trying to say, is that the more milk you make per unit of greenhouse gas production, the more efficient you're really going to be, because we make milk for food, and that's really the outcome. So same thing with methionine. So the model is capable of doing this now real time on the farm. And of course, it wouldn't be anything if we didn't show you that the model actually does a pretty good job of predicting, total protein flow out of the rumen. This is observed non-ammonia nitrogen and predicted non-ammonia nitrogen and the residuals down at the bottom. So, there's still a little bit of noise in that prediction, and people will say, well, you've got a little bit of a range there, and I'll tell you, yeah, that's probably true, but we also don't know in all of these studies what the digestibility and the rate of digestion was for all the forages that were being fed. So at this point, we're willing to accept some of that noise as long as the residuals look pretty uniform and pretty tight. We're always working to improve it. So the take-home points, crude protein is relevant here, but we got to really focus on ruminal nitrogen balance and NP supply. What I tell people is the rumen nitrogen balance should always be at least 110%, but ensure adequate nitrogen intake in the face of variability. NP balance should be greater than ME balance by about 5%, so 105% of the ME. Urinary nitrogen excretion should be as low as possible, and that should be a function of forage availability and inventory while maintaining the rumen nitrogen balance. And what we find is once the extra nitrogen is removed from the diet, starch levels will most likely increase to fill the void. Once you take something out, something's got to go up, so you enhance microbial yield. But again, it gets you back into a circle where you increase the demand for rumen nitrogen, to go back and look at the ruminal nitrogen balance. And then, once you've got the non-productive nitrogen removed, the methionine and lysine should be balanced for the updated ratios, met at 2.6% of the MP, and lysine at 7% of the MP with that 2.7 to 1 relationship. And just coming back to this, we're looking at 1.12 to 1.14 grams of methionine per mcal of metabolizable energy. And just a couple other things. ANDFOM should replace NDF and will provide more accurate predictions of ME and MP. And I didn't talk about this today, but we're moving towards the U240 or the UNDF, which is done on a 240-hour in vitro. That's going to help us out too. And then the UN assay, for those of you who really want to focus on balancing for amino acids and are feeding a bunch of protein feeds that don't fit the detergent characteristics, things like blood and fish and some other things, that assay is really helping us get better answers, and that can be directly translated into the ADIN input, and everything will keep moving. So with that, I'll take any questions.
This is Kathy Barrett again with the ProDairy program. I want to thank you for viewing this segment of Thursday Dairy Update. On your screen, you should see some helpful links if you're interested in further information.